And then we've not even asked whether Fabian's here. He is here, obviously. So over to you, Fabian. If you'd like to introduce yourself and tell us, basically, you're working for G Research now, having been at the Mathematical Institute at Oxford, where some of this work began.
Yes, that's right. Thanks. Yes, I was a PhD student at Oxford working with Tesco on modeling customer behavior in supermarkets. And then after my PhD, when the pandemic then started, I came across RAMP and then volunteered for RAMP for using some of the work on some of, I guess, the framework to adapt these models, or to model basically how COVID might transmit in supermarkets, and how the customer behavior could be modeled together with the COVID-19 transmission. And that's kind of the work that I will be presenting today. So yeah, this is together with Nifo Cleary, who's at UCL. And in this kind of project, Tesco was not involved, was only involved in my PhD program. Sadly, they didn't, they were not involved for this. And so, yeah, so when we set out with this project, we had the following research questions. One is, what is the risk of transmission in supermarkets? We hear, I mean, supermarkets are one of the places where everyone still has to go, even during a lockdown. So it's obviously very relevant question to ask for the modeling of the spread of transmission. Then looking at sort of the store layout, is there a store layout that minimizes the risk of transmission, or that could reduce the risk of transmission? The third question we wanted to look at is, how many customers should a retailer allow into their stores to reduce transmission, or to for that. And then and the fourth question we wanted to answer, but we haven't really looked into that at all, is how do different types of store compare in terms of the risk of transmission. And maybe today what I would tell you would possibly is a bit disappointing in that, since we didn't really quite have actual synthetic data, we really just talk mainly about giving a framework for how to answer these questions. And with better data, perhaps one could try to actually form a more conclusive answers to these questions. And yeah, so what is our approach in modeling this and trying to estimate the risk of transmission? So we use an agent-based models of customers in supermarkets, where firstly we coarse-grained the store into basically discrete zones, represented by a circle here. Each circle represents a small zone of maybe 2 meters by 2 meters in a supermarket, and then we connect up these zones by edges, and it becomes sort of a network where basically then customers hop around the store as they do their shopping. And this is how customers walk, and how do we assess or estimate the risk of transmission? Here we only assume customers get infected by being close to an infected or infectious customer. And indeed, and therefore, and when they're close, the definition of close in this case is when they're in the same zone, basically. So it's quite a coarse-grained model for estimating that. But the hope is that such a coarse-grained simple model can be still useful, and it can be easy. You can quickly simulate different scenarios to estimate that. And when we assume how do the customers move, we assume customers have some sort of basket. In our case, we just give some random baskets with a specific distribution for that basket size, which is not normal, which is based on previous work from a different group that found the distribution of what basket sizes are, basically. And in our work, we assume that people have random baskets, but with actual data, one could actually just use empirical data for their baskets. But in our case, we looked at synthetic baskets. Given a basket, we simulate customers moving the store, where they have a route, maybe in this case, the shortest route around the store that visits each of these items, which have the where the customer buys items. And we have some parameters in our model, but one is the arrival rate, how quickly do customers come into the store. We see how many customers come into the store per unit time. How long they stay at each node before moving to the next one, and basically the percentage of infectious customers, what percentage come in infected, and a transmission rate, which tells us basically given how much time, what's the rate at which people get infected. when they stay in the same zone as an infectious customer. And then, so this is actually quite a simple model. We just we can run this and simulate this, and then get get some parameters in the end, or get some estimates for transmission risks, for example, at the end. And this is all done in Python, and the code is all online that one can try to do it. Maybe a few notes on how do we actually do this kind of store, given a store layout, for example. So actually, no, before that, we talked a little bit some of the base assumptions, then I come quickly on how we actually, what data we had. The parameters, so quite a few assumptions of our base model, at least, is the following. So one is we assume that customers behave independently from each other. So they each have sort of a path around the store, and they take the path regardless of what other customers do. That can be extended, and one can have more like customer aware customers, or paths that are customer aware. But in our model and our results that I would talk about today, the customers behave independently from each other. We have customers stay at each node at sort of a random amount of time, which is distributed according to an exponential distribution with a mean tau, which is given here. And transmission and we assume here that transmission only occurs to customers being in the same node. So we don't assume that there's a transmission based on someone coughing and then moving away and then someone coming in. So we assume more when they're in the same zone. And transmission probability is proportional to the exposure time. And here we talk about sort of the cumulative exposure time. So how long in a shop have they been in the same zone as a different customer? And it could be split over several kind of meetings with an infectious customer. And that's perhaps not too unreasonable, given there's, I guess, some papers talking about that. It's no longer just 15 minutes being at the same place with someone like consecutively, but even if you're just with someone with 5 minutes and then 5 minutes at a later time, you still have, I guess, maybe similar amount of probability of being infected. Although I'm not sure how, I'm not sure whether there's, I guess, some scaling factor or not. But in our case, we just assume the transmission probability is proportional to the exposure time. That is the time that customer spends in the same zone with an infectious customer. So yeah, this is our model. These are parameters. What is the data that we have? We were kindly provided some data, or some synthetic data from the Sainsbury's group, who also volunteered for RAMP. And what we've basically given is a layout where we have shelves, which are in gray, and some places where customers enter, in this case, three entrances in yellow, tills where people pay, and then red is the exit. So this is the data that we had. And what I then did to, or what we did to make it into a kind of discrete store network is we put some zones on top of it, like this. Quite crude in that sense. And then each of these zones become nodes, and then we connected up neighboring ones. And that's how we created our store network. Now, okay, to some results. So with this kind of agent-based model, you can measure, really anything you like. And things that we can measure, for example, is the total exposure time. What's the total exposure time summed up over all the customers that have been coming to a store for a single day? In our simulation with the parameters that we had, we saw about on average in simulations about 94 minutes total exposure time, which is an hour and a half, but that's across all the 2,000 customers. If we looked at only, let's say, the exposure time for each exposed customer, we see that actually on average most customers have only been those that have been actually exposed to an infectious customer only been exposed for half a minute or so. And only like 18% of them have had exposure with infectious customer. Obviously, this very much depends on the parameters that we chose. We chose, in terms of the percentage of infectious customers, we just used the data from the Office of National Statistics at that time when we published the paper. But it obviously quite depends on that. And we can see what the number of infection is per day for that store, which is quite a small number. However, I guess if you sum that up over a lot of stores, then that may become significant, depending on also the parameters that you have and also the store layout you have, how big the store is. In our case, we just have one single synthetic store. One can look at the distribution of exposure time. Sorry for the picture quality. And one can look at, for example, the exposure time is sort of almost exponentially distributed across different customers. So this is the distribution of the exposure time over customers. And we see there's hardly anyone who has more than 2 minutes of exposure time with customers, with an infectious customer. And then here you can also look at the histogram of the chance of infection across customers and across simulations. Actually, no, what I'm plotting here is the mean chance of infection across different simulations, across 1,000 simulations. And I mean, it's quite narrowly distributed around 10 to the minus 11 in this case. So yeah, one can look at different things. Another thing one can look at with our model is to look at potential hotspots and bottlenecks in the store. So looking at a store layout, one can see where does the exposure happen. And here we basically we look at the total exposure time for each node. And we see towards the center of the store is quite a lot of, is high exposure time, and also near the tilts, which is perhaps what you expect, and perhaps different if you change the layout, then one can rerun these simulations and see whether that kind of helps, or that might help. Looking at some parameter sensitivity analysis, I guess, we're also looking at maybe just changing the parameters of our model. So if we one thing we wanted to look at is, what happens if we restrict the number of people in the store, and what we plot on the left-hand side here is just on the horizontal axis, just how many people you allow in, 10 to 20, how many people can be in the store at a given amount of time, and then how many infections sort of per day you would expect. We see firstly it plateaus at some point, which is not surprising, given that at some point, if this is large enough, this kind of constraint doesn't do anything anymore, because we assume the arrival rate is fixed. So we never really have more than 20 people in the store. But then we also do see that if we halve the number of people, so if we 20 only allow 10, then it does reduce it by quite a bit, by a factor of, I guess, 0.25 or something like that. Another thing one could look at is, now instead of keeping the customer arrival rate fixed at that point, what if we reduce how many people can get into the store at any time? So if we let people in slower in some ways, then it also kind of reduces quadratically, I guess. Obviously, these kind of things we can't just kind of say, okay, it's just let fewer people in, because people still need to shop. So there needs to be, I guess, some balance to trade-off to be struck. So it's hard to tell from this kind of picture how many people one should let in as well. One can also look at the chance of infection, not just how many numbers, but also if we divide, basically, if we normalize by how many customers get into the store, we see a sort of a linear kind of change, or a linear scaling from how the chance of infection is based on these two parameters, either how many people you allow into the store, or the rate at which you allow people to get into the store. So another thing we wanted to look at is the sort of store layout. And the one thing we did test was to look at what if we had a one-way layout. This was quite a popular suggestion. I think some stores have implemented, or maybe have still implemented it. I'm not entirely sure. And so to check that, to test this, we basically converted our network into a directed network, which meant that the customers can only walk along the directed edges along the store. So the path that they would previously take would now be outed to only adhere to this kind of directed layout. And then we reran our simulations and see how does that change the chance of infection, and then as well the number of infections that we estimate from our model. And I kind of just manually changed this to one-way street, where we have sort of a circle going this way, and then a circle here, and then some places where you can go both ways still, as people needed to get to the tilts. Oh, and what do we see? Well, what's interesting, so on the left-hand side, we see the rate of, so the number of infections per day as a function of basically how quickly you let customers in. And we see actually that the one-way layout has some higher number of infections than the original layout. And And actually, if you think about it a little bit longer, it's actually maybe not too surprising, at least given our model, because if we have a one-way layout, people would on average take longer for their shopping, and therefore more customers are in the store at a given amount of time, which meant that therefore you have more infections per day. If we instead of having on the x-axis the rate of customer, but instead the mean number of customers in the store, so if you kind of only look at how many people are in the store at the time, then these two curves collapse, and perhaps it means only what matters is how many customers should be in the store, rather than maybe what the stair layout. But the important consideration is if you do a one-way layout, people may take longer for their shopping because they have to take these detours around the store, and we'll have more people in the store, which means you have more, we're more likely to get infections. Yeah, so that's it about the results. There, as I said, quite a lot of limitations to at least this kind of base model, customer paths being independent of customers. In our case, the coarse graining, which means that the precise distance and even the direction of travel between customers is not taken into account. One of the, I guess, arguments for doing a directed store layout is to say people don't face each other anymore. That's not taken into account here. We assume, again, that the chance of infection is proportional to time spent in the same zone, which again may not be the case. We use homogeneous arrival rates or fixed arrival rates and shopping paths as well as all results being on synthetic data sets. So as I was saying initially, it's more a, I guess it's laying more the framework for how to estimate things, and we can make the model more precise and more realistic. And what really needs is to have some actual data, supermarket layout data, and ideally also some basket data to try and get some more realistic results. But yeah, in summary, we just presented a simple agent-based model to estimate infection risk in supermarkets based on exposure time. We showed kind of how to use the model to test different scenarios, including restricting how many people can be in the store or reducing the arrival rate, as well as the one-end layout. We've published the source code on GitHub, as well as the Python package. You can install that and try it out yourself. And we have a paper published in PLOS ONE, as I mentioned, that you can also refer to. And then lastly, our model has been, so this kind of source code has been picked up by some students in Aalto University that have then tried to extend this using more realistic pathfinding algorithms, where customers try and find the shortest path to the next item based on the A-star algorithm, for example. They have made a dashboard to it as well, and then looked at some also path avoidance where the customers avoid other people. But there's not this, so it's mainly a sort of software development work from their side, not so much research. But if you're interested in this, feel free to check that out as well. And that's yeah. So yeah, that is all I wanted to talk about. Yeah, thank you very much, and I'm looking forward to questions. And I can see there are probably some, but I will leave it to the host.
Super, thanks, Fabian. We'll hold most of the questions until the combined Q&A at the end, but as we've got a few minutes until the scheduled start time of the next talk, let's take one or two now. So Dominic C, not the one who's currently testifying to a joint parliamentary select committee, but Dominic Connor wants to know, tending to a limit with the number of customers allowed in the store is interesting and unintuitive. How does that compare to observed data?
Thanks. I just realized my internet connection wasn't very good, so I hope some of the talk was still being able to, I guess.
I heard it all fine. Yeah,
audibly.
Okay.
Tending to limit with the number is how does so observed data? That's. Yeah, I'm not sure about observed data. That's the kind of problem, that I don't really have any observed data, or maybe do I misunderstand the question? I'm tending to limit. Oh, I see. It's okay. Now I see. So basically, the limit doesn't mean it's not a realized limit. It's a limit towards how many people you allow in the store. But if only at most 20 people are in the store, then putting a limit of 50 doesn't do anything. Therefore, that's why it tends to a limit, because we fix the rate at which customers go into the store, and basically you never get to a point where you have more than a certain number of people in the store.
Okay, thanks. Let's take Sarah's question now as well. So Sarah says, are there plans to include store workers in the model in the future? She imagines that being in the store for longer shifts, their experiences are likely to be quite different from those of the customers.
Yeah, that's a very good point. And in fact, I guess, so two things. One is the first recorded kind of transmission supermarket was between actually a store worker and other store workers or with customers. So it's a good point to probably include that as well. So the students in Aalto University, they have put something store workers as an extra kind of worker who walks around kind of randomly. So this kind of extension does exist. We haven't done it in our research, but it's something that if you're interested, then there can be or it has been included by the students in Aalto University.
Great, thank you. Let's stick to the schedule and move on to the next talk now, but there are some more questions and I'll come back to them at 2:50 when we should have about 25 minutes for a combined Q&A discussion session at the end.